Hi, my name is Suleiman Panshiri. This is the fall 2022 semester for CS6263, and today I'll be giving a presentation on the paper Preventing Lunchtime Attacks, Fighting Insider Threats with Eye Movement Biometrics. So let's get started. Before I forget, I just want to make sure to give acknowledgements. So first off, to the authors, Simon Eberz of University of Oxford, Kasper B. Rasmussen of University of Oxford, Vincent Lenders of Armasuisse, Switzerland, and Ivan Martinovic of University of Oxford as well. This paper was originally presented inside of NDSS in 2015, and if you want a link to the paper, you can find it here down below, and you can read it on your own time or at your own pleasure. So, to begin, I want to talk about the overview and objectives of the paper. We can start by just talking about the purpose. And the purpose of this study is to determine the effectiveness of eye movement biometrics in order to counter lunchtime attacks. The paper starts by giving an introduction of eye biometrics, biometrics in general, and then dealing with eye tracking and gaze tracking. It discusses the vast feature space that human eyes provide compared to even other authentication metrics. And once that's been established, it's also noted the viability of current technologies and how they have advanced over the years to get eye tracking to where it is today. Next, we are shown the experimental setup and the different scenarios that may happen in a lunchtime attack. The process of the experiment is discussed with participants and repeatability, and then shows various results in image and also graph form and table form as well. And finally, near the end, the author gives credits to other related works which have had varying results of success and feasibility in their respective studies. And the end of it comes with a conclusion, providing a glimpse into the efficiency of the solution to provide the previously mentioned attacks. So now to get into a bit of background about the characteristics of eye movements. First off is the human visual system, which is the connection between the retina and the brain regions, allowing for eye movement. That movement has 6 possible degrees of motion, and those are characterized into 2 main groups called saccades and fixations. Saccades are abrupt movement of the eye between fixations, and those normally last around 10 to 100 milliseconds. Fun fact, by the way, about saccade, that's French for the word jerk, as in an abrupt movement, not the kind of jerk that you wouldn't want to be hanging around with. And fixations are different. They're what your eye focuses at low velocity, and those last around 100 to 400 milliseconds. Stability is the main goal of fixations. However, perfect stability is not possible, and the eye tends to move away from fixations in order to prevent fatigue. That's what's known as a microsaccade. Saccadic intrusions are similar, and they are a more intensified version of microsaccades where focus shifts away and then back. As you can see in figure 1, the microsaccade encloses area that is both away from the fixation point and also inside the fixation point to illustrate this. This is different from neural saccades, as those do not return to the same fixation point. Now moving on to eye and gaze tracking techniques. Eye tracking is the process of capturing a person's eye movements and measuring their positions, whereas gaze tracking is connecting eye tracking to an external display for calibration. As you can see in figure 2, this illustrates an example of gaze tracking of a subject reading a document. When comparing eye tracking techniques, there are many trade-offs. These are between temporal and spatial accuracy compared to intrusiveness and usability. The intrusiveness and usability are a huge trade-off when it comes to traditional eye tracking techniques. This is because the traditional ones involve having the user to wear a physical device, often a headset, and these can contain electrodes as well, which can interrupt the user from their daily tasks. In comparison, the more modern techniques are less intrusive, and they actually have been affecting many industries such as film and video game, which are now using eye tracking. Nowadays, modern eye tracking is dominated by video. Video-based eye tracking is often used with infrared light to focus on the eye's pupils and record the movements of it and its size. The usefulness of the infrared is in its ability to create the distinct reflective patterns. So next up, we're going to talk about insider threats. They are the adversary model focus for this paper, specifically about lunchtime attacks, which is where an adversary is able to gain control of a coworker's machine temporarily. The name comes from an attack where the coworker is away and out for lunch, but lunchtime attacks are varied. So it could be that the attacker gained access without consent, but it could also be that the attacker and the host machine's user are working together. However, these attacks are difficult to track back to the original person as they are not always using their own machine. In this study, the adversary already knows about the gaze tracking protections in place and is going to willingly try to beat them. The adversary can learn about how to beat the system in two ways: learning by reading or being instructed, and also shoulder surfing or watching how the actual user does it. So now that we've finished giving a bit of background about the various pieces of information necessary to understand the study here, we can talk about feature definition, and first off specifically about the design criteria. First off, features are all about figuring out what data is needed to collect them and being aware of potential constraints. Features must use eye tracking without relying on controlling or being aware of running applications or screen content. They must also be task independent, and they must not require controlled stimuli. The benefit of this is that the results are interchangeable with other tasks. Raw samples of XY coordinates and pupil diameter are collected and with the gaze tracking sample, and there must be groupings as individual readings do not contain enough distinguishing information to pull anything meaningful out of them. So now that we've talked about the design criteria, we can also now talk about the different types of features. Well, there are three main ones discussed in this experimental design. They are as follows: pupil, temporal, and spatial, as you can see here. Pupil features are both static and dynamic. They are in regards to the pupil diameter of your eye. And so the static aspect is maximum, minimum, or mean of the diameter, while the dynamic aspect is the short-term changes in the value of the diameter. These features are taken using the standard deviation as well as the min and max during a fixation. And next up is the temporal features. The temporal features are about the duration of saccades and fixations, as well as the speed and accurate acceleration of them. Various studies have shown that these are highly task independent, so they become a huge point of interest for this study. And finally, next up, spatial features, which are a measurement method for the steadiness of one's gaze, the distance in the horizontal and vertical directions between a pair of samples are used as points of interest here. Another important aspect of feature definition is determining the feature quality. And so being able to choose the best features and figuring out why a given biometric works are the two main outcomes of measuring that feature quality. The table on the left here, as you can see, is a measure of feature correlation by the Pearson correlation coefficient. Just for some context, 1 and -1, as you see, the extremes are representative of high correlation and their respective directions, and 0 represents no correlation, and you can see that at the middle. The study also talks more about feature quality through the use of mutual information, and mutual information is the measure of info revealed about the user ID through each feature. To compare this to the amount of uncertainty, is called RMI, or Relative Mutual Information. And so if you look here, you can see that on the right side of your screen, you have this formula where H of the user ID here represents the entropy of the user ID, and H of the user ID conditioned on F represents the entropy of the user ID conditional on the given feature. Finally, the table on the right here shows the RMI for each feature type we talked about in the previous slide. In this case, the higher the percentage, the more the feature shares information with the user ID. And so when selecting feature candidates, it is important to note that they should be hard to imitate, and the best feature set should contain features from all the different types of, as you can see here, pupil, temporal, and spatial. This is because each group provides uniqueness to the biometric. And so now we can talk about the design goals for this experiment. It is important to remember here that the purpose of the study is to figure out just how feasible it is to use eye and gaze tracking techniques as a biometric in order to prevent these lunchtime attacks. Thus, we need to find a way to design the experiment to most effectively determine this. If the experiment were to be done by letting users choose their own tasks or given a general set of tasks, it would result in a focus on different things which could be biased by the genre or different factors. Therefore, the authors of this study want to get around this by providing a specific set of tasks for all the users. This way they can determine if there's actually an inherent difference between users that are not related to the ways that they can actually complete the task. So we've just talked about the design goals. Let's talk now about the experiment structure. The experiment is set up so that one sitting of a test subject is equal to one session, where each session has 3 experiments and they're all repeated over and over. As seen in figure 5 here, the experiment is conducted again after 2 weeks, and then once again, actually an hour after the second experiment is completed. The experiments are slightly different, but they all start with a red dot with a white center on the screen at a random location, and the test subject is told to then click on that dot as fast as possible. Just a little bit more detail about each experiment individually. Experiment 1 is where the test subject has no prior knowledge about the process. They do not have instructions, and it's split between a short version with 5 dots and a long version with 7 dots. The purpose of this experiment is to replicate the scenario where an adversary does not know exactly what he or she is facing and eventually gains familiarity through repetition. That's experiment 1. Experiment 2 is a little different. This one is where the test subject is given instructions on where the dots will be before the test starts. This one replicates a scenario where the host machine user and the adversary are collaborating. The host user gives the information to the attacker so that they already have some level of familiarity before they start. And finally, experiment 3 is where the test subject is given an image of where the dots will be before the test start. This one replicates a scenario where the adversary is shoulder surfing, as we mentioned earlier. That gives us a good segue into the design validation. There are 3 metrics here to measure the task performance. Figure 6, as you can see, shows the results from these different validations. The text description and shoulder surfing experiments did not see change over repetition, and that's because the repetitions were done with identical sequences every time. So if you look, those are the red and the light blue or cyan functions on the graph. And experiment 1 tells a different story actually. If you look at experiment 1, that's with the dark blue and the green. It is seen for different validations as the number of repetitions increases. So does the effectiveness of the test subject to complete the task. This allows the authors to conclude that the test subject improves in the same fashion that an adversary might. So now we can talk about the feature stability over time. This is vital that the features remain stable because that's how we determine if the biometric is even feasible. However, there are three challenges to this. The first is the changes in the environment. This could be something like pupil diameter due to slight variations in the light of the room. The second challenge is if there's some changes to the user's physical or mental state. So for example, if the user is tired or nervous, this could affect their eye movement. And the third challenge is technical artifacts, meaning that if there are slight variations to the calibrations being done, it could affect the performance. However, as seen before with the dataset used, as training data was included from different sessions, this allows for both short and long-term challenges to be dealt with. So now just to give a bit of context on the participant recruitment before we get into the results, as you can see the experiment was taken with a total of 30 total participants from the general public. It was split between 20 male and 10 female participants. As you can see here in figure 8 to the right, 2 of these participants wore glasses and 9 wore contact lenses. And of course, this was all conducted with the approval from the University of Oxford's Ethics Committee. And now we are at the results and analysis. We have quite a lot to get through here, so let's get started. To begin, to guarantee statistical integrity, the data sets have been split between training and testing by using a five-fold stratified cross-validation. This results in 80% of the data going to training and 20% to testing. Every subject is considered a potential adversary for the other subjects, and there are actually two performance metrics used. The first is called ERR, or equal error rate. This is when the FAR, false acceptance rate, and the FRR, false rejection rate, equal each other. The second performance metric is maximal and minimal class distance. This is the distance between the template of a user and the most successful of the 29 other adversaries. As seen in figure 9 here, this is the formula for class distance. It's useful for determining how hard it is to impersonate the user. So for example, let's say the value is less than 1. This denotes an adversary is more likely to be authenticated over the actual user themselves. And a higher class distance means that it is more unlikely for the user to be impersonated. So for more on results and analysis, let's get into it. There are two classifiers here used against the data sets and feature sets. They are KNN, which is K nearest neighbors, and SVM, which is support vector machines. As you can see here in table 2, these are the results, and they show us quite a few things. As you can see, for almost every feature and data set, the SVM performs with the lower EER. In fact, the full feature set results in the lowest ER, and the reduced feature set is in second, and finally, without the pupil diameter, performs the worst of the three. This is a trend that appears across the different data sets, whether it's in the intra-session, inter-session, or the 2-week data set. And for the full feature session being used, this actually would prevent the adversary to try to bypass a few different distinct features. The authors note that as the complexity of an imitation attack grows rapidly with the number of features that have to be emulated, this underlines the resilience of the system against such attacks. In addition, the more samples there are, the smaller the EER. And now for our final slide on the results and analysis. As we've seen so far, the results of the experiment have been mostly promising. As seen in figure 10, about 92.2% of attackers are able to be detected within the first 40 seconds. And also 2.76% of attackers are failed to detect due to the similarity of their biometrics with real users. The authors mentioned that this almost 3% failure rate could be combated if they were to use a second biometric system alongside this one. They also mentioned the caveat that this wouldn't work for blind users, but as this is a pretty small minority of the population, they mentioned that this is still a huge leap forward and a potential for a new universal authentication mechanism. So before we get to the conclusion, I just want to give brief mention to the other related works in biometrics that the authors pointed out here. You can see the first one is fingerprint scanners. That is in reference to reference 31 and 32 given in the paper. And this talks about the fingerprint scanners that are present in phones. Although they may be convenient to keep, let's say, the average Joe away, if someone's able to create a mock finger, which has been done before, then the biometric no longer protects as intended. Next up is for facial recognition. It is mentioned how it's convenient for continuous authentication. However, it's not feasible for high security situations due to the imperfect liveness detection, such as through the use of photographs or 3D models. These ones come from references 33 and 34 in the paper. Next up is mouse movements, which are actually another behavioral biometric technique. From the study it came from, which is from reference 39, they promised low EER, but the data for the study was from the PCs of the test subjects themselves, so it may not distinguish well between input devices and the subjects. And finally, another interesting biometric that they discussed was through the use of electric currents in the human body. And the reference here is number 43 in the paper. That one actually discussed 100% accuracy over a static data set and 88% accuracy over one that was collected over multiple weeks. However, this sample rate is considered extremely low for the ones they had, and so it's not conclusive enough to be determined feasible, at least as of yet. And in conclusion, we can draw a few different ideas from this study. The first is that eye movements, specifically the features presented, provide a rich source of distinguishing information with an equal error rate, or EER, of 3.98% for a single session. In addition, task familiarity does provide measurable advantage to the attackers. However, it's not enough to bypass the eye tracking biometric. Finally, the results do show potential for a great primitive to build on top of for future continuous authentication mechanisms.